Alright, now practice quiz. And problem number 1. Do long division to get that result. So let me give you a minute on that. Okay, 30 seconds more. Oops. Alright, so let me set up the long division. There's a missing x squared, so I put plus 0x squared. There's a missing x, I put plus 0x minus 4. And then I'm going to put 2x plus 1 out here. And then what do I have to multiply 2x by to get x cubed? Think of it as two separate problems. To get the number correct, I have to multiply 2 by 1/2 to get 1. And then I need 2 more x's, so x squared. So then multiply these two together, and I'm going to get x cubed plus 1/2 x squared. Because of those 0 placeholders, things will line up correctly now. I subtract, and I subtract by, I like to add a negative. It's negative 1/2, oops, let me switch back. Negative 1/2 x squared, bring down plus 0x. So then I say, what do I have to multiply 2x by to get negative 1/2 x squared? It's missing an x, but the number part's more challenging. I'm going to need it to be negative, and I'm going to need it to be 1/4, and then the extra x. So 1/4 times 1/2, that'll become 2/4, which is 1/2. Alright, so multiply this, and I get negative 1/2 x squared minus 1/4 x. I subtract. I'll subtract by making it adding the opposites. Come straight down, these cancel out. This gives me positive 1/4 x. Now this has same degree as that, so I keep going. Keep going until it becomes a smaller degree. So then I'll bring down the minus 4. What do I multiply 2x by to get 1/4 x? Well, it's got to be positive. And then 1/8. And that'll give me 2/8, which reduces to 1/4 x. And then plus 1/8. And then I subtract. And you don't have to do the plus and negative. Let's do it different this time. 1/4 x minus 1/4 x. These cancel out. Negative 4 minus 1/8 is negative 4 1/8. That's my remainder. So my long division is this with remainder negative 4 1/8. Or you could turn that into negative 4.125. Turn it into a decimal. Punch 1 divided by 8 in your calculator. You get 0.125. Or you could state it in other ways. But that's the basic idea on that long division problem. It had some complications in it. It had missing powers of x, and then it required all these fractions in it as well. All right, give me a little feedback on number 1, please. Oh, and thank you for reporting on the group attendance. All group leaders could do that, please. Make sure you pop into your group, say hi. So group leaders can say who's here, and then also group leaders, make sure you remind your group who's the spokesman for the day in your group. Okay, lots of different types of feedback, which is very nice. And let's go to number 2. Solve this absolute value inequality. Excuse me. Okay, 30 seconds more. All right. So the first thing we're going to have to do is isolate the absolute value portion. This plus 1 can't be over on the same side with it. So I move that over. Okay. So once I have the absolute value isolated, I get myself oriented and I think of, all right, what's, if I had a really simple problem, absolute value of x greater than 2, what does that mean? That means distance from the origin has to be more than 2. Means I'd have to be over here or over here. And I'll remind myself, how do I get these two intervals from this? Drop the absolute value, put the word or, now this one's going to correspond with this side over here, and then you put drop the absolute value again, I have to flip the sign and negate the number. So that's what I'm going to do over here. Drop the absolute value, and that's the first one. That corresponds to this part on the right. Or, and then drop the absolute value, flip the sign, negate the number. Then I solve each of these separately. And I divide by -3, and I have to reverse this inequality. So this becomes x less than -4. Now this one, here, subtract 2, divide both sides by -3. When I multiply or divide by a negative number, I have to switch the inequality. That reminds me to switch it. X greater than 3 goes into 16 5 times and 1 left over. And negative divided by negative is positive. And this is my solution right here. And it didn't say put the answer in interval notation, so this would be fine. I could leave it like this. If it had said also put your answer in interval notation, it would look like this. From -infinity to -4, union 5 1/3 out to infinity. It'd be on a number line, it would be the left, everything to the left to -4 and everything to the right of 5 1/3. Okay, so either of these forms of the answer would be fine. Okay, give me a little feedback on number 2, please. I imagine that one was not a simple one. Let's come to this next one. Graph this. 30 seconds more. Alright, so let me have you stop. And I probably didn't give you enough time to finish this one. But hopefully, I gave you enough time that if you had a sticking spot, you got to that spot where you were stuck, and this will be instructive. So here's my XY grid, and at 2, the world changes. There's going to be one rule to the left of that red dotted line, and a different rule and a different function to the right of that red dotted line. Let's look at the first one. If I take y equals 3x minus 1, and I'm going to graph that. Now there's a couple ways I could do that. I could say the y-intercept is -1, put a dot here, and the slope is 3. Means it rises 3, 1, 2, 3, when it runs 1. And I could, graph this. I could also graph it like this. I could make x and y, plug in any point I want. Let's suppose I plugged in 0. And then I would get -1. And then a crucial point you have to plug in is the boundary point. Even though you're not supposed to plug in 2 into this, if the input was 2, we'd find that the output was 4. You don't plug it in here, but we need to see how close we need to get, what the target value is over here. Because x could be 1.999999, and it can get infinitely close to this target value. Now we're going to we plug it in here, we get 6 minus 1, which is 5. But this, I'm going to remind myself, it's got to be an open circle when I graph it. Okay, so I'm going to put these 2 points, 0, -1. I already had a dot there. And then 2, 5. This one we had said make sure it's an open circle. Now when I connect these 2 points, it'll go through that other point that we had already seen. And this will go infinitely far in this direction. Now the other part is y equals 4 when x is 2, 3, or 4, or anything, you always get the output of 4. And we put 1, 2, 3, 4. We start with a big open circle, and then I see, because it's the equal sign, I fill that circle in. And then the other points are at the height of 4. It goes horizontally forever. Like this. Alright, a little feedback on number 3. And the more details, the more I can adjust. Like, for instance, need more practice, I'll tend to put more practice on this. Or really got this down, I'll tend to not put more practice. So the more details you can give me, the more I can respond to them. Okay, so this one was a little bit easier one. Yeah, there are some more complex ones. Okay, and state the domain. Thirty seconds more. All right. So if x is 3, it causes the numerator to become 0. But that's not a problem. Top of a fraction can become 0. The problem is if the bottom of a fraction is 0. What x's cause the bottom to be 0? Can't be 1. It can't be -4. That's the domain there. Now if I asked for it in interval notation, it would look, but that's fine because I didn't ask for it. But if I asked for it in interval notation, it would be -infinity to -4, union -4 to 1, union 1 to infinity. Okay, give me a little feedback on number 4. Alright, number 5 and number 6. Do 5AB and 6A. And 30 seconds more. Alright, so on A, well, let's go to B first. B means the same as this. It's really an unwritten 1 there, and you could call this 0x. And when you made a table for it, what it means is if you put y as any other number but 3, you can't get this to work out. Y has to be 3. But x can be whatever it wants. It can be 1, it can be 5, it can be anything. This, I tend to think of this as height. the height has to be 3. So the graph is a horizontal line through 3. And how does that differ from this one up here? This is saying the x-coordinate along the x-axis has to be 3. But the y could be any height, because it's going to be plus 0y. The height just gets zeroed out. So this one is a vertical line. X equals is always a vertical line. Y equals always a horizontal line. The degree of this polynomial is the highest power that occurs on the variable. So this is just degree 5. And if we go to this one then, this one would be degree 3. Highest power that occurs on the variable. Alright, give me a little feedback for 5 and 6. Those are some basics that I just wanted to make sure that you had, because we're going to need them today. And if it's been a little while, maybe you need a little refresher. Alright, so today's section's kind of got a lot of material in it, so I don't have a lot of time for answering questions. But if there's any quick questions, well, let's take those now. Any questions on the homework or anything prior? Yes.
So on the homework we had last time we met, there's another formula for the dividing polynomials that you didn't teach us. Like when I was doing it, to do it the other way, and I forgot what the name of it. But it was telling us to do it another way.
Oh, for the long division?
Yeah.
Ah, yeah, that's called, let me flip back there. I'm forgetting the name of that too. Synthetic division. Alright, yes. And I did not teach you synthetic division, so you do not have to use that. And some of the problems, I see why it says to use synthetic division, but no, you don't have to use synthetic division. You can just use the division that I showed you. Okay?
Okay.
All right, good question. I should be making a note.
I already know how to do synthetic division. Can you do it?
If you want to know how to do synthetic division?
No, if I already know how to do synthetic division, so can I use it?
If you already know, yes, you can use it.
Okay.
Yeah.
Cool.
Yeah. And generally speaking, if you prefer a different method of doing anything than the way I teach it, you can always use any method you want, as long as you can consistently get correct answers. There's lots of different methods for lots of different things. And I'm not married to my techniques at all. Whatever works for you, it's great. Any other questions? All right. Then, well, let's move on to 5.6, rational functions. All right. First of all, definition of a rational function. My instinct, if I was first learning this, would be I would think of rational like, a rational human being is someone who's thoughtful. So rational functions must be like thoughtful kind of functions or something like this. But that's not at all what it means. What's a rational function? It comes in math, it means something different. It comes from this part of the word, ratio. And a ratio means a fraction. And so a rational function is a polynomial divided by a polynomial. Now, what's a polynomial? Polynomials look like this. They'll have a variable, and they'll have only whole number exponents to the variable. And it could have lots of different powers. So, polynomials divided by polynomials, that's what a rational function is. Now, polynomials do have these things called degrees. The degree of the polynomial is the highest power in the variable. Yeah. We're going to be looking at rational functions, polynomial divided by polynomial. So look at this one, 1 divided by x minus 3. The 1 is still a polynomial because we can think of 1 as 1x plus 0. And so it's 0x plus 1 is the same as this one right here. And so it would be the highest power. We could even say, because anything to the 0 is 1, we could even say that that's a 0th degree polynomial. And that's a first degree polynomial. So it's a polynomial divided by a polynomial. Now, if you put y equals 1 divided by x minus 3 into a graphing calculator. Now, by the way, if you put it into a graphing calculator, you'd have to put parentheses. If you go 1/x minus 3 in a graphing calculator, it will only divide the x by the 3. If you want both of them divided by 3, or 1 divided by x minus 3, it'll only divide the x by 1. But if you want both of them in the denominator, you'd have to put in parentheses. There's an implied parenthesis around numerator and denominator when you have a long fraction bar. Okay, so So when I use the graphing calculator to get this graph, I'm going to get something that looks like this. And it really looks strange. And students are often kind of overwhelmed at first, and they say, whoa, I'll never be able to understand this. How do we get such a crazy graph from such a simple looking function? All right. Well, that's what we're going to figure out today, and we're going to, by the time we're done today, you should have a fairly reasonable feel for this and not be at all surprised that this is the shape of the graph of this function. And there's a couple features on this graph that I want to point out. There is a vertical and a horizontal asymptote. Now, a graphing calculator won't show either of these asymptotes, but what they are is the vertical asymptote is a vertical line that the graph gets closer and closer and closer to. And right at 3, we have such a vertical line. And this graph over here is going to hug up to that dotted line and get super duper close to it, but never touch that dotted line. And the graph over here on the left is going to zoom in closer and closer to that vertical dotted line and never touch it. That's vertical asymptote. The other thing I wanted to point out is it has a horizontal asymptote. There's a horizontal line at a height of 0. this horizontal line, this graph is going to zoom in closer and closer to a height of 0 and never touch it. Same with this one. It's going to zoom in closer and closer to the height of 0 but never touch the height of 0. Alright, so those are some basic definitions. What's a horizontal and a vertical asymptote? And we're going to see today how when you have rational functions, polynomials divided by polynomials like this, how we tend to get horizontal and vertical asymptotes in such cases. Alright. We will wind up memorizing the following two things. And vertical asymptote. What input causes the denominator to be 0? That's the question you will ask yourself every time you see, every time you're looking for a vertical asymptote. Similarly, for horizontal asymptote, you will ask yourself, as the input gets super large, what happens to the output? Alright, so, because we're going to be memorizing this, I want you to do a memory exercise right now. Look at both of these definitions until you feel like you have them memorized. Then look away from the screen and write them down from memory. So look at them long enough until and try to memorize both of them so that when you look away from the screen and write them down, you write both at one time without having to look back at the screen. And when you're done, you can look back at the screen to check how you did. So let me give you a minute to do that right now. Okay. If we were physically in class, I would have you pair up and I would assign one person to say it out loud to the other person. So hearing it, as well as writing it, as well as speaking it, all helps in the memorizing process. We want to memorize these two phrases, these two questions for vertical asymptotes and horizontal asymptotes. Alright, that'll be just a first step. Now, let's look at vertical asymptotes. And let me bold this here. So we have to have some prerequisite skills first. Without a calculator, state whether the following fractions are big or small. So, in your group chat, for this first one, type in, but don't hit enter yet, whether this is going to turn out to be a big number or a small number. 6 divided by 0.001. Alright, go ahead and hit enter with either the word big or small. Alright, and now I am going to show you that this turns out to be big. Why is this big? Well, 6 divided by 0.001. Division. When you're in elementary school, you learn there's 8 kids, there's 8 cookies. You need to split them up to 2 kids. So 8 cookies divided into 2 piles is going to be 4 in each pile. But when you have decimals, that kind of thinking doesn't work. 6 cookies in 0.0001 kid, I mean, you can't figure that out. We need to generalize this. And so how we think of division in a more general way is, how many times larger is 8 than 2? It's 4 times larger. Now, asking how many times larger is the same as, how many of these do I have to add to itself? I have to add 2 to itself 4 times to get to 8. That's why. That means 8 is 4 times as large as 2, and so that's why the answer is 4. So this is 1/1000th. How many times do I have to add 1/1000th to itself to get to 6? So I add 1/1000th to itself 6,000 times. Because you add 1,000 times just to get to 1. 6,000 times. So that's why the answer is big. The answer is 6,000. And we're looking at the ratio. How many times bigger is this than this? Or how many times do I have to add this to itself to get to that? Alright, next one. Do the same thing. Is this answer? Type in big or small into your group chat. Don't hit enter quite yet though. Okay, hit enter. Alright, this one turns out to be small. How come it's small? Well, the smaller number on the top, how many times bigger is that now? It's smaller than that. You're going to get really, really small. In fact, when you divide by 10, you move the decimal 1 place to the left. When you divide by 1 with 4 zeros, you're going to move this decimal 4 places to the left. 1, 2, 3, 4. You're going to get something really small. Not decimal. So you get 1, 2, 3, 4, 5. You get something really small when you do that. And next one, big or small? And go ahead and hit enter. And this one is big. Why is it big? We're looking at the ratio. This one is a lot bigger than this one. This is only 3/100ths. Now this is way smaller. That's tenths, 100ths, thousandths, 10,000ths. That's 1/1,000,000th. You have to add it to itself 1,000,000 times to get to 1. You don't have to get it all the way to 1, but you're going to have to add it a bunch of times to get to this. So it's the ratio of the sizes here. Okay, and then 0/8, big or small. And then the last one, 7/0, big or small, the last two. Alright, so I'm gonna hit enter into your group chat and your answers for those two. And group 3. What do you have for 0 divided by 8? Is it big or small?
I'm not sure on that one. I popped out of the window so I couldn't even see the problem. It wasn't allowing me to even see what you're doing. So I got kicked off. So it needed a minute to look.
Okay, struggling to even see your window. Sorry about that.
Yeah, that's okay.
Let's go to group 2. Big or small for 0 divided by 8? Okay, hopefully your group leader has told you who the spokesman for the day is. So, group leader is Aiden. Are you there, Aiden? How about the backup? Annika? Are you there?
Yeah, I'm here. It would just be 0, right? So small.
0, small. How could we check? To see if,
Just
yeah?
0 divided by 8. It's just 0.
It is 0. And on this one, 8 divided by 2, we say that that's 4, and we can check our answer by multiplying these two together. 2 times 4 gives you 8. And this one, when we multiply these together, 8 times 0, yeah, 8 times 0 is 0, so this is small. Okay, and what about this next one?
And that undefined? That's what I was thinking.
We could say undefined. And if we had to choose big or small, which would we choose? Big or small?
Big.
Big. Why big? Well, let's look. It's
Because the number on top's bigger than the denominator.
the number on top is bigger than the denominator. And if we also use that other thing of to figure out how many times bigger is, how many times would you have to add 0 to itself to get to 7? Well, you add it an infinite number of times and you're still stuck at 0. It is so big that even putting infinity isn't good enough. That's why we call it undefined. It's too big. And so even infinity doesn't make sense, because in that sense then an infinite number of zeros added together should give you 7. So we didn't have any choice, but we had to call this undefined. Okay. Now let's go to the next. Oh, now we'll continue at this point after we take our break. So we're at break time. So we will start again. At add 15 minutes, it's 1:34 p.m. Okay, and does anybody need to speak to me individually before I take my break?
Mr. Shankin?
Yes.
This is Destiny. I just wanted to say that I may not be here next Thursday.
Okay. Hey, thanks for letting me know. And
Yeah.
if you could send me an email right before, like next Wednesday, to remind me of that, and I'll have the video up, later in that same day, so you can always look on the video.
Okay. I already did the homework for that day.
Oh, super. All right.
Because I'm getting my wisdom teeth taken out next week. That's why I'm not going to be.
Say that again. You're going to have your what? Wisdom teeth?
Yeah.
Oh, wow. All right. Well, good luck
So,
with that.
That's why I'm not going to be there.
Yeah. Okay. Okay. Thanks for letting me know. Anybody
Yep.
else? All right. I'll take my break too. All right, well, let's get back to it again. Let's look at these. The sequence is getting closer and closer to what number? So, look at this sequence. Go into your group chat. And type in what you think the sequence So think of each of these as, 7 divided by 100 is a number. So each of these are numbers. And what is this sequence getting closer and closer to? All right, and hit enter. And this sequence is getting closer and closer to 0. Why is it? Well, we had talked about as bottom, see, notice what's happening. The top number is staying the same, but the bottom number is getting larger and larger, making the total fractions smaller and smaller, and we're going to 0. You can also see that it's going to 0 because the sequence is really this. If I put it in decimal form, dividing by 100 moves the decimal 2 places to the left. And then divide by 1,000. We're getting closer and closer to 0. Okay. Now, look at the next one. Type in to your group chat. What is this getting closer and closer? What number is this getting closer and closer to? And let me ask group 1. What is this getting closer and closer to?
Infinity?
Very good. Because the top number is staying the same, but the bottom number keeps getting smaller and smaller. So the ratio is getting larger and larger and larger. 5, 50, 500, 5,000 kind of stuff. And so we are going off to infinity. Alright, so now now this is all on the topic of vertical asymptote. Vertical asymptote example is an experimental race car. And this is kind of a science fiction-y example. The race car is being tested on a 2-mile straight road. Early versions of the car were terrible. Complete the chart below. So, the first thing is it took 1 hour for it to get the 2 miles. So, how fast was it going? Fill that in. And then it took 1/10 of an hour. So after they took it into the shop and tinkered with it, it was 10 times faster. And it only took 1/10 of an hour. And then how fast was it going then? Alright, so fill in both of those. And enter your answer into your group chat. And hit enter. And group 3, how fast was it going in the first case?
I don't know. Nobody else answered it. I personally don't know.
You got any idea, Jordan?
No.
No. Okay. How many miles did it go? Well, it went 2 miles. And how long did it take? 1 hour. So its rate would be 2 miles per hour. Now that's the rate at which you go on a slow walk. So this experimental race car was really bad. It took a full hour to do the 2-mile straight line road, and it was a bad vehicle. Now, what formula am I really using when I do this? Well, the idea is distance.
Isn't that slope formula?
It's kind of similar, but it's really this one. Distance equals rate times time. And the distance was 2 miles. And now we're going to modify this a little bit because we're trying to find the rate over here. So we're going to take and divide both sides by time. And these will cancel. And what I'll get is rate equals distance divided by time. And the rate's in miles per hour, so it kind of makes sense. This is distance in miles, time in hours, and we just do that and we'll come up with these results. Alright, so I'm going to have you fill out the rest of this. Compute how fast the race car was going in each of these situations. And enter your answers into your group chat. And reminder, if you can't come up with anything, but stuck, but you gotta put something into your group chat. I'm gonna be checking on that as part of your participation, and you get a participation grade. So just not putting in anything is not okay. Putting in that I'm stuck or I'm not sure what to do, that's always fine. Okay, so examine the other responses in your group chat for a moment. Group 4. What do you have when it's 0.1 hours? What rate?
20 miles an hour.
20. And how did you get the 20 miles an hour?
I just did this. Well, since that since that 2/1 is 2 miles an hour, and we just moved it down 1 decimal place, I just multiplied it by 10.
Great. And it's 2 miles in 0.1 hours. If you punch this out in your calculator, you would get 20. All right, and so what's the next one going to be?
200.
200. Since it's 1/10 the time, you got to be going 10 times as fast. And then this next one?
2,000.
2,000 miles per hour. All right, so what we're seeing here is if we kept this going, the same pattern going, what's this getting closer and closer to? Getting closer and closer to 0. What's this going to get closer and closer to? As this gets closer and closer.
Infinity.
Yes, it gets closer and closer to infinity. That is correct. And the equation is right here. That equation led to this vertical asymptote right here. And now we want to go to this. Remember, I told you to memorize this. What's the question? Don't look back at your notes. Do the best job you can right now of reconstructing what's the question that we ask for a vertical asymptote. Do you remember a little bit about it? And the same thing for the horizontal asymptote. I'm going to be asking you these repeatedly throughout the day to reinforce the memory. The more we use it, the more we won't lose it. Right. So what's the question that we ask for a vertical asymptote? It was, let me scroll back up here. Vertical asymptote. And let's review both of them now, because I'm going to be asking you both of these during class today. So what input causes the denominator to be 0? Give yourself a pat in the back if you could remember at least part of that. All right, and let's review the horizontal asymptote question. As the input gets super large, what happens to the output? All right. But what input causes the denominator to be 0? That's the question that we ask for vertical asymptotes. Now let's come down to here. What's the input that causes the denominator to be 0? Now, here was the equation. It's when this denominator t is 0. As t gets closer and closer to 0, the fraction gets incredibly large, goes off to infinity. It turns out that 0 is not an allowed value in this fraction. If it took 0 hours, no time at all, to go from one end of the track to the other end of the track, then you would have traveled faster than, this would have been, faster than light speed travel. Poosh, you'd have just, it's kind of like Star Trek, beam me up kind of thing here. But we don't have any math that really models that instantaneous travel, because we'd have dividing by 0. And we can say as we get closer and closer to 0, this gets closer and closer to infinity. But when we put 0 in there, an infinite number of zeros added together never gets up to 2, so that fraction doesn't exist. All right. Now, let's now go back again to look at this. I had told you that way back earlier, y equals 1 over x minus 3. Right there. That its graph is going to look like this. And we identified the horizontal and vertical asymptotes in the graph. Now we're going to get some insight into this. Why in the world did the graph turn out so crazy looking? Well, let's take a table. And start looking at some values. If I put in 10, what am I going to get? 1/7. It's a very, so if I put in 10, here's 1, I'm going to get very low on this. As I move back closer and closer, let's go to 5. I'm going to get 1/2. If I get to 4, I'm going to get 1/1, which is 1. Now, I can't put in 3, because if I put in 3, I get 1/0, and that's undefined. That's not allowed. But let's put 3.1. I'm going to get 1/0.1. So how many 1/10ths do I have to add together to get to 1? I need 10 of these. So as I get close to 3, I get really large. One over 0.01, which is 100. I get even larger. The closer I get to 3, the larger I get. So this is why we put a vertical asymptote at 3, and what happens is we zoom in tighter and tighter to that. We never cross this dotted line. If you cross the dotted line, it would give a value to the function when the input is 3. But when the input is 3, it's not allowed. You can't have an output. Alright, so we're starting to get a little insight of why that crazy graph looked so crazy. Alright, let's look on the other side of this. Suppose I put in some different values. Suppose I put in 0. And I'm going to get 1 over -3 or -1/3. So here's -1, like here. And as I go to 1, I'd get 1 over -2, -1/2. And get a little more space here. If I put in 2, I get 1 over -1, which is -1. And I'm not allowed to put in 3. But if I put in 2.9, I get 1 over -0.1, which is -10. If I put in 2.99, 1 over -0.01, which is -100. So what happens over here, I can make this in blue as well. On this side, we also get closer and closer to this vertical asymptote. And we never touch a vertical asymptote. It has to do with, again, these sequences of numbers. We're getting sequences that are getting larger and larger because the bottom of the fraction was getting, see, the top stayed the same, but the bottom, 1 over 1 over 1 over, the bottom kept getting smaller and smaller, driving us bigger and bigger, like this. Okay. Any questions? So
it's a reflection, right? If you're looking at the vertical asymptote, and then on one side you have one
yes.
reflection.
Yeah, one side goes up to infinity, the other side down to -infinity.
They kind of lean on the vertical asymptote of 3 on either side.
Right.
Don't cross it.
Okay, now that's going to be the case most of the time. If you had something like this, y equals 1 over x squared, that one is a crazy one when x is 0, it's undefined. As x gets really close to 0, this fraction gets super duper large. But since x squared is always positive, it would be going up on both sides. So there are times when a vertical asymptote can have it going on both sides, going to infinity, or both going to negative infinity. And that's only when there's an even power involved. Alright, so find the full equation of each vertical asymptote. So let's look at this first one. Now, once again, what is the question you ask when trying to find a vertical asymptote? See if you can answer it to yourself without looking it up. So the question is, what input causes the denominator to be 0? And the answer to that question will give you the full equation of the vertical asymptote. Now, to answer that question, I might be tempted to say, oh, x equals 0 is going to cause the denominator to be 0. But x equals 0 causes the denominator to become 2. That's not. There's a specific input that's going to cause the denominator to be 0. Now, you might be able to just look at that and be able to tell. Ooh, it's got to be a negative number, and you might be able to figure it out in your head. But if you can't figure it out in your head, you would just write down this equation. What is the solution to 5x plus 2 is equal to 0? And then I'll solve this. Divide by 5. When you solve this, this gives you the equation of the vertical asymptote. I'll call it VA for vertical asymptote.
So the vertical asymptote in that one is negative 2/5. Is that right?
2/5. That is correct. All right. So if we were to graph this one, we would have like negative 1 over here. Negative 2/5 would be, between 0 and negative 1. It would be over here. That's the value at negative 2/5. That's the value that we could not put in to a table. But as we got closer and closer to it, the function is going to go either zooming way up or zooming way down on either side of this. Okay. Notice again, this x equals something. This goes back to the practice quiz. X equals was always a vertical line. Y equals was always a horizontal line. So vertical asymptote is going to be an x equals something. Alright. So we're here. Let's go find the full equation of the vertical asymptote for this next one. Alright, let me work this out. I could get this. Let me think about this for a second though. First of all, if x is 0, it causes the numerator to be 0. That's not a problem. I want what x causes the denominator to be 0. I can figure that out if this is in factored form. And while it's not in factored form, I can't tell what x is going to cause this denominator to be 0. So I'm going to say I can factor a trinomial by putting an x here and an x here. These two things multiply together to be x squared. When you factor, don't do the numbers next, do the signs next. And it does not work like this. Some students think, oh, since it's a plus and a minus, it should be a plus and a minus. But you think of it this way. These two numbers that are going to go in the second slots have to multiply to be a negative. Since they multiply to be a negative, you can't have them both the same sign. If they're both positive or both negative, they'll multiply to be a positive. So it has to be one negative and one positive. And it could be in either order. Doesn't matter. Okay, now these two numbers have to multiply to be 36. And since they're opposite in sign, when you add them together, they have to add to be 5. In other words, they have to subtract to be 5. And since the result of the middle term is positive, I want the larger one to be positive. So I can think of two numbers that multiply to be 36, that when I subtract them I get 5. That'll be 9 and 4. And I want the larger one positive. 9 times 4 is 36. The two middle terms will turn out to be negative 4x plus 9x, which is plus 5x. So I'm going to replace this with its factored form. So then, my vertical asymptotes, there's two of them. What x causes the denominator to become 0? X equals 4, and x equals negative 9. When x is 4, you'd get 0 times 13. 0 times 13 is 0. It makes the whole denominator 0. Alright, so this one, if we were to be graphing this one, we would be making at 4 and at negative 9, we'd be making our vertical asymptotes. Any questions here? Alright, let's go to horizontal asymptotes. So, once again, test of your memory. State the question we ask for a horizontal asymptote. See if you can write it down without looking at it. See if you can just get a part of it. And if you're like me, you have a horrible time memorizing something until you understand it. And so the question that we asked for horizontal asymptote was, as the input, gets super large, what happens to the output? Alright, that's the question we're going to have to memorize. Now, let's look at a specific situation. McDonald's advertising in a specific city. So, McDonald's realized that they have a whole bunch of McDonald's restaurants in this city, but they don't have it up on any billboards, and they haven't done any advertising over here. And what they did was they noticed that, geez, with no extra advertising, their sales were down here. And so they spent a little bit of money and put some billboards up, and whoop, their sales, and each of their, their total sales in the city went up. And then they did a bit more. And then they carefully tracked the results and found out, yeah, the sales went up again, up to here. All right, so go to your group chat, and what do you think if they kept putting more and more money into advertising, more and more, and lots of billboards in this specific city, what would the shape of this curve be? And I'm going to call on a group in a minute, so I'll give you a minute. You can start typing it in at any point now into your group chats. What kind of shape of a curve will we get here? Alright, so I'm going to ask group 1, since these 3 points kind of lie in a straight line, will it be a straight line just going up forever and ever and ever like this? Or do you think it'll be different?
We were thinking a curved upward, an upward curve.
So would it get more and more upward, going up and up steeper?
Oh, hold on, let me check in with my group.
Okay.
We're thinking yes.
It'll get steeper and steeper as we go. Like this. Like that. Okay. And what's your name?
Nika?
Nika? Okay, great. And you know, if you can remember, not a huge deal, but if you can remember, just, you know, state your name real quick before you start talking, it'd be great.
Okay.
It's just one of the limitations in Discord is we don't get to see who's talking otherwise. All right, that's a great start. We're thinking maybe it'll go up like this. Anybody else have another idea what the sales might look like if you spent more and more on advertising? Thinking of the practical situation. Okay. No other.
I'm guessing it might plateau, right? If all of a sudden you started spending 0 on it, that might happen, right? You might end up with a 0 all of a sudden because the sales would go to 0 if you spent 0 on advertising. I'm just taking a guess. I don't know.
Ah, okay. So let's look at this. One of the words you used there was plateauing. And it might do something like this. Go through these 3 points and then level off like this. And in fact, if this was a real situation like this, we would expect it to plateau or level off like this. And you would get less and less returns on your spending on advertising. What would happen in a situation like this is, yes, the first few billboards are going to like put McDonald's, you know, they'll get the craving, oh, I gotta have a milkshake, I gotta, you know, and more people will stop. But then they'll get to, you might call it kind of a saturation point. Yeah, if they're reminded enough, it's not gonna do much more good. You spend and put a lot more billboards up, and just people are just so much McDonald's they're gonna wind up eating. And you're going to get less and less returns. And so what this is actually a horizontal asymptote. And we tend to find these naturally occurring, the plateaus that we kind of rise up towards, and then, now horizontal asymptotes are different than vertical asymptotes. Vertical asymptotes you can never cross because it gives a value when the denominator is 0. And that function doesn't have any value when the denominator is 0. Sometimes horizontal asymptotes get crossed. You might have a little blip, you know, it goes up over it a little bit, but then it settles back down towards it. And it's just the tendency, and now we're starting to see, remember this definition, as the input gets super large, what happens to the output? As we spend more and more on advertising, oh, this reaches a ceiling that it doesn't really cross. Just gets closer and closer to that ceiling. All right. Now, same kind of thing happens. Number of ants in a home that gets X ounces of insecticide. So, the pest control company might have taken some data and says, you know, here's a typical home in Santa Fe, and we only put this many ounces in, we've wind up seeing ants decline from about here to here. If we put this much pesticide in, we get less ants, like this. What do you expect to happen? At first you might think, well, it looks like it's a straight line, so it's just going to come all the way down. But in actuality, when we connect these, you put more and more pesticide and you get less and less results. And you still are going to have some ants that are still going to come in from the outdoors, even if you got tons of pesticide. And it'll reduce the number, but it doesn't get rid of them altogether. We wind up getting the horizontal asymptote is the x-axis itself. Horizontal asymptote at y equals 0. Now, we get actually an equation. Now, vertical asymptotes, their equations were x equals something. Horizontal asymptotes are horizontal lines. Horizontal lines are y equals something. When something is like, you know, and when a population of zebras in the world is going down to, you know, they're being exterminated, they might get down close to 0. But we keep a few in zoos and stuff like this, so that it doesn't quite go to 0. All right? It gets close, really close to the horizontal asymptote. All right. All right. Now we're running out of time, so I'm going to have to jump over to state the horizontal asymptotes of this one right here. As x gets super large, what's happening to f of x, the output? The output goes toward, well, let's look. We've looked at these patterns before. The top number stays at 1. But what happens to the bottom number? It keeps getting bigger and bigger and bigger. When x is 100, you get 1 over 98. When x is 1,000, you get 1 over 998. These fractions get smaller and smaller. As this goes to infinity, this goes to 0. So the horizontal asymptote is y equals 0. Now, what we're seeing is the numerator did not grow, but the denominator kept getting bigger and bigger. And that forces the total fraction smaller and smaller down to 0. All right, let's look at the next one. As x gets super large, now we'll shortcut that by putting it like this. As x goes to infinity, g of x also goes to infinity. As x gets bigger and bigger, g of x also gets bigger and bigger. So this means there is no ceiling there's no horizontal asymptote. It just, if there was, you're trying to make a barrier at the top, it would just crash right through it. And this one, as x goes to infinity, f of x, alright, as x gets larger and larger, does the top grow? Nope. Does the bottom get bigger and bigger? Yep. So as the top stuck and the bottom gets bigger and bigger, the whole fraction goes to 0. Horizontal asymptote, y equals 0. Alright, and we have more to finish up on this, but we have run out of time. So the homework is, I want you to start this section 5.6 and do the vertical asymptote portions. We didn't get quite far enough in the horizontal to really answer the horizontal asymptote parts of the questions. So just get going with those, and you can just upload that into the spot check, and that'll be fine. You don't have to have a full 75%. We'll finish this up next time so that you completely can get the horizontal aspect.
So which one's for the spot check again? I'm sorry, Robert.
Just, you know, there's problems throughout the whole thing that says find the horizontal and vertical asymptotes. So just do the part that is the vertical asymptotes.
Okay, cool. Thank you. Okay, let's do that.
All right, and then do the vertical asymptote parts, save the horizontal asymptote parts till we've done that next time. All right, we will stop here. Any questions? All right, let me stop the recording.